Welcome to the seventh lecture of the second half of the course. So far, we have formulated boundary value problems in terms of stress. And in your part one, you have formulated boundary value problems in using displacement formulation. And we have also looked at special cases such as plane stress and plane strain problems. And we have seen that in the absence of body forces, both of them both these problems, when stress formulation is used, end up with the same governing equation, which is the biharmonic equation. Now, we have determined it in terms of in the Cartesian reference frame. Okay, even when you do the same analysis in the polar coordinates also, you will still end up with the same biharmonic form, which is del power 4 times phi is 0. We will look at the general solution in the polar coordinate system, right? What is the general solution? General solution, say for example, y double prime plus y is equals to 0, or a second order differential. This is a general equation, right? Not this is not necessary. So let me add a here, right? Now I'm going to seek a solution. Let y is equals to lambda power x, right? So if I substitute this answers here in the given equation, I'll get lambda square plus a times e power lambda x is 0, which means my lambda is minus whatever that is, which is square root of minus 8, which means plus or minus, which means my general solution is y is a times exponential root of minus a times x plus b of exponential minus square root of minus a times x. So this is the general solution. Depending upon the boundary conditions, I should be able to identify a and b. So for this kind of equation, y double prime plus a times y is equals to 0, this is the general solution. Now we have an expression del power 4 times phi, which is either a function of r comma theta is 0, or as we have derived in Cartesian reference frame, del power 4 times phi of xy is 0. We want to look at the general solution of this, of first starting in the polar form. Maybe in the next class, we will look at the general solution in the Cartesian frame, right? So this is what we mean by general solution. So we will identify the general solution of Airy stress function in polar coordinates. Let's begin. Before we do that, let us see what happens without a body force and with body force. How does that expression of biharmonic equation change? Okay, some the derivations which we have done so far are when there is no body force or when the body force is equal to 0. So we had this particular governing equation, right? And in a compact form, this is how you write it. And what did we say was the procedure? You solve for this with the boundary conditions, and that is the reason we are in the process of developing the general solution, right? And once you know phi, you can evaluate the remaining three quantities which are essential in a boundary value, or which is the goal in the boundary value problem. So how does one solve for phi is something what we are looking at right now. Now, how do these plane strain and plane stress problems change, or how does the governing equation change once there is body force? Okay, so I'm going to assume that there's a body force of bx, by, and bz in 3 dimensions, but now you're looking at planar problems, so basically bz is 0. Okay, and body forces are conservative in the sense, if the object happens to undergo displacement in a circular path or in some path and it has ended up in its original position, then the net work performed by the force is 0. Basically, there is no loss. So this is how we will define body force. Bx and By are the components. And since body force is a conservative force, it is possible to write it in terms of another potential V. Just the way we wrote for stresses, we identified Airy stress function, which is basically the stress potential. What is the use of a potential? Using a potential, you can derive quantities whichever you need, right? Since body force is conservative, the mathematics will tell you that it is possible to have a potential V, which is called as potential function. And this is how it is defined. Bx is negative of partial V by partial X, and By is negative of partial V by partial Y. The negative sign is coming because this is a conservative field. Otherwise, you will end up with a plus. Okay. And now this is how we will define the stress functions. Previously, when body force was 0, the potential was essentially 0. So now I'm going to add that potential here. And whereas when it comes to shear, I'm not going to include anything. Right? This is how I'm going to define. And the remaining procedure is the same. How do we say, what do you mean by same? We start with the equilibrium equation, right? In 2-dimensional case, instead of sigma ij, if it is 3-dimensional, you will write your sigma ij comma j plus bi is 0, right? And when it is 2-dimensional, the notation is alpha and beta. Something which you have learned in your part 1, right? What is the starting point? This guy is the starting point, the strain compatibility equations. And then you write the strains in terms of stresses, okay? And then you use the equilibrium equation, right? And you do all this mathematics for plane strain, you will end up with this kind of formulation. Likewise, you do it for plane stress, you will end up with this as the governing equation. As you see, if the body force is absent, which means the potential V is 0, which means both of them, this will be 0 as well as this will be 0. This is a straightforward algebraic expression manipulation. So I suggest that you should formulate your plane stress and plane strain problems with body force and try arriving at these expressions. Okay, it will be a good exercise for your learning as well. Since the fundamentals have already been established, what is new in the last 2 lectures compared to this particular slide, only this term is new. Everything else is the same, right? So I would suggest that you do this, right? And you should, you may take half an hour time to arrive at these expressions, but that is fine. You take half an hour, you take 2 hours, absolutely no problem. That should not be your criteria or how long you have taken to arrive at these expressions. It's just that you should go through this process of using the same formulations that we have developed and arrive at these expressions. Okay, so now let us proceed with our goal of general solution for the biharmonic equation in polar coordinates. So far in cylindrical coordinates, in Cartesian coordinates, we have been nicely writing this as dou, oh no, why is this guy coming? 5 by dou y power 4 plus 2 dou power 4 by dou x square dou y square times 5. This is how we have been writing in Cartesian form, right? And what is del power 4? Del power 4 is del square times del square, right? And what is del square? Which is something you can look up in any engineering mechanics or elasticity books. So del power 4, the fourth derivative of phi is this in an expanded form. Okay, you can check this expression as well. So for this expression, which is looking slightly complicated, we will identify the general solution. So let's proceed. This is our expression. We are looking for how is the form of phi of r comma theta. This is the goal. And we seek what is called as a variable separable solution. What is ansatz? Ansatz is the form. What is the form? Like in the first slide, when we looked at the general solution of this guy, second order derivative of y with respect to x and a times y is equal to 0, we chose an ansatz of this form. or we sought a solution of this kind. So this guy is the ansatz for the first problem which we solved. Now we will seek a variable separable solution, as in I will have this as some f of r times say g of theta. So this is the form we are looking at. And this has been first proposed by a scientist named Michel. Okay. Since there is the second derivative of theta being involved and there is no first derivative of theta, the derivative with respect to theta is either theta square or is either it is the second derivative or it is the fourth derivative. Okay, so it's multiples of 2, and that is the reason the experience of solving partial differential equations will tell you it is okay to choose this kind of function as sum of sinusoidal and cosine function and some function of r. So this is the variable separable form which we are seeking, right? And sine and cosine are both harmonic functions, right? And so since they are harmonic functions, you can start off by saying let this be the general solution or f of r times sine n theta be the solution. Either way is fine. You can start with the left hand function or the right hand side function. Either way is fine because sine and cosine are both of them are harmonic functions and you are dealing with second order derivatives, second and fourth order derivatives with respect to theta. So since this is the ansatz, so let us take these any of these expressions and substitute it in the general in the governing equation. That's what we are doing. Substitute this in the biharmonic equation and we will identify the characteristic equation and its roots, and let's see what we get. So remember this form f of r times cosine n theta, and we'll substitute this in the first expression. So all I did is replace phi with f of r times cosine theta. Right? Now let us do the partial derivative. F of r is independent of theta and cosine n theta is independent of r. R and theta are my variables. F of r is independent of theta, cosine n theta is independent of r. So the partial derivatives are relatively straightforward. And I'm using the superscript f I I. I'm using the I, this each of these I for the derivative with respect to r. Since this is second derivative, this is what I'm saying. It's just a compact form of indicating the derivatives, partial derivatives. Okay, so straightforward simplification from here to here. All this is the second derivative, this is the first derivative, and f of r is as it is. I'm taking the second derivative with respect to theta. So first derivative will give me n sine theta, and the second derivative, first derivative will give me minus n sine theta, and the second derivative with respect to theta will give me n cos theta. So that's why I get minus n square. Okay, and then I'm going to expand it. I mean, do the same derivative process once again, and I will end up with such kind of fourth order differential equation with respect to f and a cosine theta term. Okay, so here to here, first to this step to this step is derivative with respect to this. Then the next one is I have just expanded, multiplied these expressions, and I have taken the all sorts of derivatives which are being assigned. So now you have a fourth order differential equation with respect to f. In fact, this is nothing but d square f by dr square. F, the superscript, f is only a function of r. So there is the partial derivative with respect to r is same as the actual derivative with respect to r. So this is the equation that we have ended up with. How do we solve this? This is a fourth order differential equation and a cosine term, right? So cosine n theta, if it is 0, which means where is cosine n theta? How did this fellow come? We chose phi of r theta is some f of r times cosine n theta. If cosine n theta itself was 0, then your phi is basically 0. So that is the trivial solution. We are not looking for trivial solutions, right? So this term cannot be 0. Hence, this partial differential equation must be 0. So now we are left with solving a partial differential equation purely in terms, not even a partial differential. This is now an ordinary differential equation in f with the derivative as r. And now I am seeking a power series solution. F is a function of r. I have a partial differential equation. Fourth order. I'm sorry. This is an ordinary differential equation, right? F is only a function of r, and the derivative is with respect to the variable r. So now I have an ordinary differential equation in f with the variable as r, and I am seeking a power series solution or simply series solution. And that's why I'm saying let f of r be r power m. Okay, so I'm simply going to plug it. This is something which we have done when we are solving the plane strain problem, where we were solving a long cylinder pressurized internally and externally. So if I do this, is what I get. I'm taking the fourth derivative. This is the first term. I'm taking the derivative of f 4 times. Likewise, I'm taking the derivative with respect to r 3 times. So likewise, I'm doing it for the remaining terms. That is all. Simply plugging in this ansatz in this ordinary differential equation. Okay, let's move ahead. If you notice, the coefficient, the power of r in all these terms is r power m minus 4. Okay, so the power is m minus 4. So r power m minus 4 is a common term in all of them. So I'm going to pull that term out. Okay, so this term is actually multiplied with r power m minus 4. Right? And r is anyway not 0. Correct? We're not looking for the trivial solutions. Trivial solutions are ruled out. So which means this is the expression which is equals to 0. Right? I'm going to factorize it, and doing that will give me either m is plus or minus n, or it is 2 plus or minus n. Let us not lose sight of things. What is n? Where did n come up from? We had phi of r theta is f of r times cosine n theta, right? This n came from there. And we said f of r is, so this is r power m. So this is the solution which we were seeking. And now we got a relation saying you cannot randomly choose m and n. M and n should be governed by these relations, which is plus or minus n and 2 plus or minus n. Okay, we have chosen a power series with respect to r, and that coefficient need not be independent. That's what our differential equation is telling us. You cannot randomly choose m and n. If you pick a value of n, correspondingly these should be the values for m. Okay, let's proceed. So we are going to choose different values of n. N starting from 0, 1, 2, 3, and so on. Okay. Why are we choosing integers? Because we are we are kind of looking for a Fourier series with respect to theta. So when n is 0, what is the value of m? In the first case, it is 0, and the second case, it is 2. And in either case, you will see you have double roots. For example, when n is equals to 0, you get the value of m as 0 and 0. And likewise, in the second case, you get the value of m as 2 and 2. So these are double roots. So you know what happens from that previous problem that we solved when you have double roots. When n is 0, what is cosine n theta? 1. Sine n theta is 0. Right? Sine of 0 is 0. So this is the form for phi which we chose, right? And f of r is r power m, which means my f of r is the following: a01 of r power 0, which is 1, right? And due to the double root, you get the logarithmic term. Then a03 of r square, and due to the double root in 2, you get it as logarithmic of r. How does this logarithmic term come from? It comes from the mathematics of power series solution. That is why if you are interested, you can look up any book on partial differential equations. Any advanced engineering mathematics book should be of help. Okay, so we got this form of radial function, and the theta function is as it is. So which means this is how your phi of r theta will look for n is equals to 0. So we are done with only the first term. Let us go ahead and look at n is equals to 1. So I'm just rewriting the same thing. N is equals to 0. This is the solution. And in 19733, which is relatively new when we speak in terms of research, a scientist named Little said, apart from these 4 terms, you also get another term where the radial function is the similar form, a constant, a logarithmic term, an r square term, and an r square times logarithmic term multiplied by theta is also a solution. This is what he has found out. Going by your usual power series method, you will only get the first 4 terms. But Little in 1973 has proved that these are the additional solutions which are possible. Hence, we will also account for these terms. Okay, so now look for, let us see what happens when n is equals to 1. If n is equals to 1, what is m? M is plus or minus n and 2 plus or minus n. So when n is equals to 1, you get minus 1 and plus 1. And when n is equals to 1 for the second expression, you will get it as 1 and 3. So you are seeing 1 is the double root. Right? So this is minus 1, r power minus 1. This is r power 1. And r power 1's double root. So we are multiplying it by the logarithmic function. And this is r is equals to 3. And cosine n is 1. So cosine n theta will be cos theta. Sine n theta will be sine theta. Right? So let us write the whole full function. Before we write that, let us also account for the terms which the scientist Little has also identified. Apart from your 4 terms, apart from your 1 by r, r, l, r times log r and r cube terms, you also have another set of 4 terms which will also satisfy provided you multiply them with theta everywhere. Okay. And those are the additional terms which we will account for. So your expression when n is equals to 1 is basically this. This is the solution when n is equals to 1. Okay. It is long, but it looks long, but you will see as you solve problems that these expressions are very handy. Instead of every time we solving a 4th order partial differential equation, especially in polar coordinates, this is much easier when we have the general solutions. We simply need to apply the boundary conditions and we can get rid of most of the terms. And then when n is equals to 2, you will get m, the following values for m. And once you know m, you can identify f as r power m. And that's how you get these 4 functions for f. And accordingly, you will get another 8 terms. Okay. Slight correction, there should not be this infinity. Okay, or unless I am looking for terms. So let me say 2 plus. I am looking for n greater than 2 because you have this summation. It is only this. If we are only looking for phi 2, phi 2 of r theta, then you substitute for r as whatever you have. Okay. Now I've gone one more step ahead and said this is for n greater than 2. This is how your solution will look like. That is what I tried to show here. Even here 4 terms of sine and cosine. Okay. So if you look at your overall expression, these are the terms for n is equals to 0. These are the terms for n is equals to 1. And these are the terms for n greater than or equal to 2. In the previous slide, what did I write? Yeah, this is n greater than or equal to 2. Okay. So this is what your general solution for the biharmonic equation in polar coordinates looks like. Okay. How many coefficients does it have? For n is equals to 0, you have 8 coefficients. For n is equals to 1, you have how many? 1, 2, 3, 4, 5, 6, 6 and 6. So you have 12 coefficients here, looks like. Right? And for every value of n greater than or equal to 2, you have 8 other terms. So should I worry about these many terms? If I just consider n is equals to 1 and 0 itself, I'm getting some 20 terms. Yeah, most of the time it is sufficient if you consider n is equals to 0 or 1. You will see with experience, you will know whether you should consider the higher order terms or not. Okay, but overall for this complicated fourth order partial differential equation, which is also biharmonic, this is the general solution. So any time when we want to solve a plane stress problem or a plane strain problem without where there is no body force, right? So when you want to solve a plane stress or a plane strain problem, and if in that problem there is no body force, and if you are resorting to using polar coordinate system, you directly use this solution. You don't have to reinvent the wheel. I have done this derivation because as engineers, we are bound to know the details. At the same time, we should be ready to apply whatever derivations we make. Okay, that is why I have shown you the derivation. Okay, and maybe in the future, you guys, one of you may be in a position to come up with better solutions. Okay, the theory of velocity is not completely done or played out. There is still a lot of things that needs to be done. Okay, so this is the general solution. So whenever you want solve a polar problem, plane stress or a plane strain problem in polar coordinates without body force, this is the general solution. Okay, so please go through the derivation once again. Try to do it on your own. Depending upon which book you refer to, the coefficient, people may write different coefficients in different form. That is all right, so long as the key is how the forms of the function are there. R theta term, R cube, 1 by R, all these terms. This general form is very essential, very is needed. The coefficients you can write it. I mean, some other book may write, I am writing it as A and 3. They may write it as some other term, say some B and 3. And this may, they may write it as some capital A and 3. So that's all right. Those are anyway constant coefficients and vary with respect to the physics of the problem. Okay, so from next class, we will try to solve a couple of problems using this polar coordinates. Revisit the derivation once again. Thank you.